Welcome back, Physics 30. So this is the FM1.7 projectile motion and FM1.8 combined solving projectile motion problems. So here we'll use the kinematic equations that we looked at earlier, along with the vector component method to solve problems involving two-dimensional motion of projectiles. So there's a couple of key things we can pull out of here, a bunch of tricks that we can use to solving projectile motion type questions. So a projectile is an object moving in two dimensions under the influence of Earth's gravity, and of course you can see here the shape is that of a parabola, an upside down parabola, and it could be understood by analyzing this motion. Now a couple of things to note here. So this is just a ball or a marble being flicked off of a table. If you'll notice here, the velocity vector, the Vx velocity vector going to the right, it's the same length all the way down until it hits the ground. What that indicates is that assume that air resistance is negligible. Horizontal velocity is constant. So if you throw something horizontally, it'll maintain that velocity the entire time until, of course, gravity pulls the object down and makes it stop. And of course, if it's a really fast-moving object, yeah, then we have air resistance coming into play. But if we're talking about slower-moving objects in which we can assume air resistance is negligible, we have this being true. So V is equal to delta D over delta T. That's how we can figure out what that velocity is. And quite often what I like to do to distinguish it between other movements, call it the velocity in the x direction or the displacement in the x direction. Okay? So that's one key thing to note. Horizontally, this Vx is the same all the way through. Another thing to note here is that if I just simply drop an object versus launch an object at Vx, look at where they are vertically. Same spot, same spot, same spot. You can basically take a ruler and go like this, and they're at the same spot throughout. And quite often what I do in classes, I show a Mythbusters video in which they shoot a bullet and drop a bullet at the same time. And what you find is that they both hit the ground at the same time. So it tells us a couple of things. Horizontal motion is independent of vertical motion. So what happens here is that gravity interacts with both of these in an identical fashion. They both fall at the same rate. That's kind of a key thing to note. So we can say horizontally launched objects and dropped objects at the same height fall at the same rate. So if we wanted to analyze the flight pattern of a horizontally launched projectile, all we have to do is analyze a dropped object, and they have the same time of flight. Same time of, instead of saying flight, I'll just say time of fall. That's a key thing to note. And of course, it's a lot easier to analyze this. We've already done this back in FM1.5. Analyze the time of fall of a dropped object. So we can do that with this scenario here as well. Okay, so those are key things to note here. So horizontal velocity is constant throughout the whole path. And dropping an object or launching it horizontally, they fall at the same rate. They have the same time of fall. So since it isn't moving along the ground, well, in the air, the speed of an object in the x direction is constant. So yes, just like what I said over here. Since there is little friction working on it, we assume that air resistance is negligible, and of course that only that happens at slower speeds. If we get at higher speeds, air resistance may play a part in it. Other than that, we don't have to worry about it. And then if I look in the y direction, of course, it experiences the acceleration due to gravity from g. And here's basically another picture showing it the same thing. Same spot, same spot, same spot. So vertically, they fall at the same rate. If I was to look at it this way too, going to the right, I would see that these lines would be evenly spaced apart, indicating constant horizontal velocity. So the photograph on the right shows two balls that start to fall at the same rate. The one on the right has an initial speed in the x direction. It can be seen that the vertical positions are identical at identical times, while the horizontal position increases linearly due to a constant speed. And an object projected horizontally will reach the ground at the same time as a vertically dropped object, as I mentioned. If an object is launched at an angle equal to theta naught or theta 0 with the horizontal, the analysis is similar, except that the initial velocity has a vertical component. So even here, launching at something vertically, or at an angle, Vx is the same throughout the entire time. So horizontally, delta v, or v is equal to change in d over change in t. And if I want, I could call it Vx and displacement x. It's equal to the same. And it's, of course, projectile motion is motion with constant acceleration in two dimensions where the acceleration is at and is down. Let's look at this example. A child sits upright in a wagon which is moving to the right at constant speed. That's important. The child extends her hand and throws an apple straight upward from her point of view, while the wagon continues to travel to the right at constant speed. The air resistance is negligible. Where does the apple land? Does it land in her hand? Does it land behind her? Does it land in front of her? Well, if this is true up here, if the horizontal component is independent of the vertical component, if I have a wagon going to the left at Vx, then my angled ball will be going to the right at Vx as well. So guess what? When viewed by someone on the ground, the apple has an initial horizontal component of velocity equal to the constant horizontal velocity of the wagon. So to the person on the ground, the apple follows the path of the projectile and experiences no horizontal acceleration. Therefore, the ball, let's put not stays, but continues with constant velocity Vx equal to the constant horizontal velocity of the wagon. Okay, I kind of got long-winded here, But you can think of it too, like in your car, if you're sitting in the back seat of your car, you're going at 100 kilometers per hour on the highway, and if you throw a ball up in the air, you catch it. It doesn't fly back behind you. It doesn't fly in front of you. It lands directly in your hand because the ball is going with you. Now, if you were sitting in a convertible and threw a ball up in the air, then yes, it would land behind you because air resistance is coming into a play. If you're going at 100, if you have a ball going at 100 kilometers per hour, or if you stick your hand out of the window going 100 kilometers per hour, you feel that air resistance on your hand. So in that case, the air resistance isn't negligible. But if you're inside your car, your ball definitely travels the same horizontal speed as you. All right, so we'll stop there and we'll come back and do the next part. All right, we'll see you again.